What if the next leap in AI came not from bigger models alone, but from smarter ways to make them think, move, and learn? In today's episode, we dive into three fascinating ideas: looped transformers that turn efficiency into an advantage, a unifying neural flow framework that connects finite and infinite dimensional learning, and the hidden role of condition numbers in making GLU networks train faster than their non-gated counterparts. Together, these papers reveal how theory and architecture are reshaping the future of AI. Let's explore the first paper, LT2 linear time looped transformers. LT2, or linear time looped transformers, replaces the quadratic softmax attention bottleneck in looped transformers with subquadratic token mixers while preserving weight sharing across iterations. The paper studies LT2, linear, built from linear attention primitives such as gated delta networks, GDN, KDA, and Mamba2 style recurrences, and LT2, sparse, built from sparse attention such as native sparse attention, NSA, and DeepSeek's DSA. The key novelty is that looping is not just compatible with efficient mixers, it amplifies them. In the linear case, repeated application upgrades a rank, one memory update into an effective rank T update. And in the sparse case, T-loops expand a sliding Windows receptive field to roughly T times W tokens. On FineWeb Edu, pre-training at 0, 6, B, and 1, 3, B parameters with T equals 4, LT2 variants stay within about one average zero-shot point of the full attention loop, while LT2 hybrid GDN plus DSA matches the standard looped transformer at 1, 3. B, perplexity 9.72 versus 9.87 and reaches 125 tokens, S decoding at 8K context, about 5.7 times faster than the 22 tokens, S baseline. The strongest model, LT2, hybrid full plus GDN, improves average zero-shot accuracy by 2.1 points to 61.39 and achieves 2.7 times faster decoding, establishing a new quality efficiency Pareto frontier. A converted 1. A 4B model, oral hybrid 1. 4B, obtained with about 1B continuation tokens, outperforms industry-level 1B models and approaches 4B class models on benchmarks, including ARC-C, Hellaswag, Winogrand, MMLU, GSM 8K, and Ruler. The paper also shows that GDN stabilizes training better than RetNet or DeltaNet, and that a simple SDPA output gate reduces attention sync compounding across loops. Let's explore the second paper. Neural flow operators can approximate any operator abstract frameworks and universal approximations. This paper introduces an abstract neural flow framework that unifies finite dimensional neural networks and infinite dimensional neural operators in a single Hilbert space formulation. The key novelty is the separation of the continuous depth model into two dynamics: a composition structured flow, whose explicit Euler discretization recovers ResNet type architectures, and a separation structured flow, whose semi-implicit splitting discretization yields plain feed-forward architectures. For piecewise constant parameters and leaky ReLU activations, the authors prove well-posedness and local Lipschitz dependence of the flow map, then establish what they describe as the first universal approximation theorem for flow-based models between infinite dimensional spaces. Any continuous operator O, Cy on a compact set C in an abstract Hilbert space can be approximated arbitrarily well by Rick theta tap, where P and R are bounded linear maps and F theta T is either flow type. They further show that the same result holds under convolutional constraints, by realizing fully connected linear dynamics exactly through constant convolution kernels. Finally, the paper transfers these continuous time guarantees to finite depth architectures via time discretization, proving universal approximation for both plane and ResNet style neural operators, as well as fully connected and convolutional neural networks. The framework includes standard models such as Fourier neural operators, DeepONet, and convolutional neural operators, but its main contribution is the unified flow-based explanation of why these distinct architectures inherit universal approximation power. Let's explore the third paper. The devil is in the condition numbers. Why is GLU better than non-GLU structure? This paper explains why GLU and its variants, especially ReGLU and SWIGLU, outperform non-gated feed-forward blocks by tracing the effect to NTK conditioning rather than to a smaller generalization gap. In a two-layer network analyzed in the neural tangent kernel regime, the authors derive an approximate factorization. K croc is approximately equal to K croc dec X D, showing that the GLU gate suppresses gradient correlation and makes the kernel spectrum more compact. Under Gaussian inputs and Lacan initialization, they prove that reglue changes the scaling of the largest NTK eigenvalue from theta min for ReLU to theta min D, while the smallest eigenvalue remains theta mines, but becomes larger than the non-GLU case. This yields a smaller condition number and therefore faster gradient descent convergence. Their experiments confirm the spectral prediction on synthetic data and on real models. Replacing FFN blocks in ViT and GPT-2 with glue variants reduces NTK condition numbers across ReLU, GeLU, GeGLU, and SILU, SWIGLU settings. The paper also derives a loss-crossing phenomenon. Non-GLU models can descend faster early in training, but GLU overtakes later because its larger lambdamin controls the slowest mode. In contrast, across MLP Mixer on CFAR, 1.0, ViT on Tiny ImageNet, and GPT-2 on FineWeb Edu, the generalization gap LTEST-LTrain remains statistically similar with and without GLU, with permutation test p-values mostly above 0.05, indicating that GLU's primary benefit is optimization speed, not gap reduction. That's a wrap on today's AI paper highlights. Thanks for watching.